So for this one, let's work number 835 here. I don't know if you can read that, so I'm going to read it to you. 835 says, heated air at 1 atmosphere and 100 degrees Fahrenheit is to be transported in a 400-foot-long circular plastic duct at a rate of 12 cubic feet per second. If the head loss in the pipe is to not exceed 50 feet, determine the diameter of the duct. So whenever they tell you to determine the diameter, that's almost guaranteed to be an iterative problem. It's going to be a guess and check problem. So in these Chapter 8 problems, when it's problem, wow. Let's try that again. Is my pen going to give out? My pen's going to give out on me. Iterative problem. Let's try that one more time. Iterative problem. Here we go. So, these are going to require a guess and check. This happens when you have to find the diameter, or if you have to find the flow rate. If either of those are unknown, the diameter or the flow rate. If the diameter is unknown, you don't know the flow rate, by the way. So if either of those are unknown, that's what the problem's asking for. It's going to require some kind of a guess and check method. You're going to have to guess, if they're wanting to know the diameter, you're going to have to guess the diameter. If you guess the diameter, then you can, if you know the flow rate, you should be able to find the speed. Given the speed and the fluid properties, you can then find the Reynolds number. Given the Reynolds number and epsilon over d, then you can find the Darcy friction factor. Given the Darcy friction factor, you can normally, and given the energy loss or the head loss or the allowable loss, then you can normally use that to find what is a good value for the diameter. And then you repeat. You repeat until we get what we call convergence. What that means is you start getting the same value over and over again as you go through the loop. It's going to look daunting. It's going to look confusing. This is what I've learned is if you will draw this roadmap. This is what I've learned over the years teaching this class. You'll draw this roadmap. Anytime you've got an iterative problem, especially if you're not used to doing iterative problems, and I don't expect you are at this point. Anytime you've got an iterative problem, draw your roadmap. And I say program because realistically, as engineers, we're out in the field, we're just going to use a computer to do this for us, or we're going to program a computer to do this for us because we don't want to do it all the time. But this is a pretty simple loop. It's pretty easy to do. If you understand how this works, then you'll understand how the computer is working and whether it's working for you or not, or you'll understand how to program the computer to do it for you. Okay? And we'll see how this works, and we'll get pretty good at it. Now, if you don't know, let's say you don't know the flow rate, but you do know the diameter. Well, you can guess the flow rate. And if you do know the diameter, but you don't know the flow rate, you're trying to estimate what would the flow rate be, well, then you can use that flow rate then to find the speed. Given the speed and the diameter, then you can find the Reynolds number. Given the Reynolds number, then you can find the friction factor. Given the friction factor and the acceptable energy loss, you can then use that to estimate what is a better value for the flow rate. And then you repeat, and you notice it's almost the exact same roadmap. And it's the two main problems. Unknown diameter, unknown diameter, unknown flow rate. In either case, Draw this roadmap on your paper. It'll help both of us. It'll help me when I grade you. It'll help you when you get lost, because inevitably you'll get lost somewhere. What the heck are we trying to do? We'll go back to the roadmap. Where are we? We just found the Reynolds number. What are we going to do with that? We're going to find the friction factor, and that gives us a better value for diameter, etc. Okay? All right. So this is page number, what do I got, 4? Yeah, page number 4. Trying to stay organized here. All right. So let's continue then and look at 835. 835 is one of these iterative problems where I'm trying to find the diameter. 835 in Changle and Symbala, 3rd edition. I know you probably can't read it from there, but I just need it over here where I can write my givens. Let's set this problem up. 835 says I've got air. It's at 1 atmosphere and 100 degrees Fahrenheit, in case I needed to use ideal gas law to find properties. I've got pressure and temperature. I do need the temperature to find properties, period, because ultimately I'm going to need density and viscosity. So I've got air transported in a 400 foot long circular duct at a rate of 12 cubic feet per second. That's volume per time, so that's a V dot. They tell me the head loss cannot exceed 50 feet. Now that probably means we've got a fan or a compressor or something like that. Some kind of device that can provide about 50 foot of head to this flow. And they're saying we cannot exceed that value. So we need to achieve this flow rate, cannot exceed this value. And they want you to find the diameter of this circular duct to move air at this rate. Okay. Some ways we can find that, given what we have. We know we've been given the head loss, and we can find the head loss based on the Darcy friction factor. Length divided by diameter. The speed, the average speed squared divided by 2g. Well, I know the length. I don't know the speed, but if I can find the diameter, I can find the speed. And the Darcy friction factor is going to be a function of the Reynolds number and epsilon over d. And by the way, they told us this is a plastic. That's going to be important to find the Darcy friction factor. So how do we use this head loss? Well, here's what the head loss represents. Can we find these other quantities? Well, if I can estimate diameter, then yes, I can find all these other quantities. So I'm going to need a guess and check method to do that. So this is what I'm looking at. All right? I'm going to guess my diameter, use that to find a speed, use the speed then to find a Reynolds number. Using Reynolds number and epsilon over d, I can then find an F value. Using F and the head loss, then I can estimate, right? If I know everything else, and my diameter becomes my only unknown here, and I can use my head loss, which I know, and the Darcy friction factor, which I can base off of this guess, to find a better guess for diameter, and then repeat. Okay, let's see if, now, there's a number of ways you could do this, okay, but this is what I like to do. I like to try to do as much algebra as I can ahead of time, okay. I know the volumetric flow rate. Volumetric flow rate, which of course is area times speed. I don't know speed, so let's see if I can solve around it. So the other expressions, basically what I'm saying is the other expressions I'm going to use here. I'm going to need to know the Reynolds number, rho VD over mu. So let's organize all the expressions we know we're going to need. We know we're going to need the Reynolds number. We know we're going to need to use this to go between diameter and speed. I'm going to use this. Okay. Well, I don't know the speed, but here's the thing, I can solve around it. The area is pi d squared over 4. So that means that the speed then is going to equal to, if I put speed as a function of this unknown diameter, the speed is going to equal 4 times the volumetric flow rate divided by pi divided by diameter squared. Right? And if I plug that in here, that means the Reynolds number, if I solve around the speed, because I don't know the speed, that's density times 4v dot divided by pi d squared times d divided by mu. That's my Reynolds number. So if I simplify this down, the Reynolds number is 4 density v dot divided by pi mu diameter. Since I don't know the speed, this is Reynolds number as a function of only diameter being the only unknown. Okay? So again, I'm trying to get rid of my unknowns. I don't know the speed, but I don't have to know the speed. All I need to know is the diameter. And so basically I've taken this step out now, right? So now I'm saying, well, here's the speed based on the known diameter. Well, let's substitute that in. Let's find the Reynolds numbers. Okay. All right, so where do we go from here? Well, let's go find epsilon, shall we? It's a plastic duct. So if we go in our text, I've bookmarked it here for ease. Plastic's pretty easy to remember a lot of times. Glass and plastic are what we call smooth substances. When they're formed, they solidify essentially as liquids with smooth surfaces. They have approximately 0 epsilon values, and we're in English units, so we'll call it 0 feet. Again, that's table, for us, that's table 8-2 in the 3rd edition. That's page 368. Okay. All right. I think we're ready to go through loop. Page number 5. So, here's the good news. Your first guess of diameter, anything is okay. There's no bad guesses. Now, a common thing to do is you look at your Moody diagram and say, well, how about I just guess it's turbulent and it's out here somewhere? Well, it's a little different with a smooth line. If we just guess, well, it's just out here somewhere, so go find epsilon over d and come back over and match up an F value over here in the completely turbulent region. But if it's smooth, it's a little while before it kind of flattens out. So you can, what that means is, again, there's no bad first guesses. And you can actually, you don't have to start here and guess an actual value for diameter. Your first time through the loop, you could actually start here and say, well, I'm going to guess the Reynolds number to be 10 times, 10 to the 7, right? 1 million, and then work through from there. That gives you an F value, which gives you a better D, and then we can repeat. You can do that. We'll go ahead and guess an actual value of diameter. Okay, that's my timer, so we're at the end of this first video. So we'll pick up there.